Hello and welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem reflection from the February 2025 USACO Bronze Contest. In this problem, we are given a square grid of dots and hashes, and our goal is to determine the minimum number of flips required to make the grid both horizontally and vertically symmetrical. For example, here, this could be our initial grid of dots and hashes, and we might want to turn it into something more like this, where you can see it's nice and perfectly symmetrical. And each flip in this problem corresponds to either taking a dot and transforming it into a hash mark, or taking a hash mark and transforming it into a dot. And here we can see sort of one corner stands out as sort of being different from the other three corners. So in order to sort of transform this into a nice symmetrical shape, we're going to try to make this outlier corner match the other ones. And in order to do that, we're going to have to flip a dot into a hash in this position. We're going to have to flip a dot into a hash in this position. And we're going to have to flip a dot into a hash in this position. And you can see we get this nice symmetrical shape in just 3 flips. And there's no faster way to do it. One way of thinking about symmetry is thinking about sort of folding the shape along the two major axes. So there's going to be a horizontal axis and a vertical axis. And if we fold the bottom half up, we can see that when we do that folding action, every hash mark aligns with a hash mark, and every dot aligns with a dot, and we get sort of this shape folded in half. Then we can fold along the vertical axis, and we're just left with this single corner. And what you can see is that this shape is just reflections of this singular top left corner. So that is our end goal, is to create a shape where if we reflect the top left corner, it matches the rest of the grid. So this brings us to our primary key observation in this problem, which is that for symmetry, it is necessary for all pairs I and j that these grid elements must be equal to each other. For example, let's suppose I and j are 0. That is simply saying that each of these corners have to be the exact same element. So what we want to do is we want to loop over the grid, and for each value I and j, we want to force these elements to be equal to to each other if they're not already. And that brings us to sort of 5 different cases here. So these 4 elements could be 4 dots. If they're already 4 dots, we don't need any more flips because they're already all equal. And the same is true with these hash marks. If they're already all 4 hash marks, we don't need any flips. They're already equal. It's good to go. Now suppose these 4 elements, one of them was a hash mark and 3 of them were dots. What is the most efficient way to make them all equal? The most efficient way is to replace this hash mark with a single dot. So that requires just one flip. If there are 2 hash marks and 2 dots, and note that these could be in any order, they don't necessarily have to be arranged precisely like that, then we could either flip the hash marks into dots, or we could flip the dots into hash marks. It doesn't matter. Both ways require us to use 2 operations. And then if there were 3 hash marks and only 1 dot, then in that case, the best thing to do is to flip the dot into a hash mark, requiring 1 operation. So to solve this problem, we can just loop over the grid. In particular, we could loop over the top left corner of the grid, check if these elements are equal. If they're not all equal, sum up the minimum number of operations needed to force them to be equal. So let's dive into the code, and then we will add one extra bit to the problem at the end. We are now ready to begin looking at the code. So we're going to start by reading in first the input. N is the size of the grid. U is a variable that we will get to in a moment. And the grid is then an n by n grid of dots and hashes. We're going to call our final output in this problem running tally. That's a bit of foreshadowing for the final component of the problem. And the first step we want to do is to loop over the grid and count how many changes we would need to make in order to make the grid symmetrical. And we're going to store that value in the variable running tally. So as we discussed when we were working out the problem by hand, we want to loop over the top left corner of the grid. So to do that, we're just going to loop over the pair of characters RC, and we're only looping over the first half of the rows and the first half of the columns. So this corresponds to the top left corner. And then we are going to write a function called count dots, which is going to return to us the number of flips required to sort of fix the position RC based on the number of dots in these four elements. And remember, the goal here is to get all those four elements equal to each other. So let's take a look here. We're going to write the function count dots. It returns the minimum number of operations necessary to make all four of these elements equal to each other. So we're going to start a count at 0, and then we're going to look at each of these elements and check, is this one a dot? 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 And then for each of those, we'll increase the count. So if ij is a dot, increase count. If I n minus 1 minus j is a dot, increase count, and so on. And at the end of the process here, count will store a number between 0 and 4, and we just have to return the right value based on that count. So if the count is 2, then we want to return 2 operations required. If the count is going to be 1 or 3, then we need 1 operation. And if the count is 0 or 4, then they're already all equal to each other, so we can simply return the value 1. Or sorry, return the value 0. And this completes the problem as we've described it so far. We count the number of operations required to make it symmetrical, and then we print out that value. However, there is one more twist to the problem, which is this value u. In addition to trying to print out the number of flips required to make the grid all symmetrical, you are also given a list of U changes to the grid. Each change is just a singular flip, and then you have to reprint out the number of operations. So, for example, in this situation, the grid required 3 flips, but maybe they give us the operation 1 comma 4, which then would flip this, and then we would have to recompute how many operations are required. So if we recompute how many operations are required in this case, in addition to flipping these 3 dots, we would also have to flip this hash mark. So we get an additional operation, and before we return to sort of the all symmetrical shape that we desired. So what we have to do here is we have to amend our algorithm so that we loop over the U changes that are being made to the grid and then print out the running tally for each change. Now, a very common mistake in a problem like this would be to recompute the count of the number of operations required from scratch. So you make a change, recompute the number of operations. Make a change, recompute the number of operations. However, this ends up being a very slow process, and you will get a TLE error if you do this. Instead, what we want to do is we want to maintain a running tally of the number of operations needed, and then just make small changes to that running tally based on the change given to us by each of these U operations. So to perform this trick, we're going to read in the spot that we're supposed to flip. So we're flipping the hash mark at coordinates r comma c, and we want to record 2 things. I want to record the number of operations required to make the grid at RC all equal before I make the flip, and the number of operations required to make them all equal after I make the flip. So I'm going to call the before case start. So I just call count dots on RC. Then I make the flip in the grid. So this performs the operation of taking what used to be a dot and making it a hash mark, or what used to be a hash mark and making it a dot. And then I'm going to recount how many operations would it take to make all of these equal. And I can do that by again calling my function count dots. So once I've done this, once I've grabbed start and end, the new number of operations that is going to be required is simply going to be the value running tally, so the old number of operations I needed, minus start, because I'm no longer using these operations, plus end. So now I require end operations to make grid RC equal to all these other values. So I lose start operations, but I gain end operations. So we're going to update running tally to simply be running tally minus start plus end, and then we can print out the running tally as we go through the program. And this completes the entire code. This question type appears quite frequently, this idea of maintaining a running count through your program. Anytime you have these types of questions, you want to figure out how can you quickly update your count without having to restart or recompute the value from scratch. So thank you so much for watching, and I'll see you in the next video. Bye-bye.